Hello, welcome to another video. Today we'll be talking about analytical limits again, but these ones are a little more moderately difficult ones so we can get really good at doing them because they're the type of thing you just need practice of doing, sort of like the harder ones, and then everything else kind of becomes not too bad later on. So let's start with something kind of similar to the limit we're doing in the past, which is one like an x squared one, but I wanted to introduce something like an x cubed one, because sometimes they do like throwing that in. So let's say we had the limit x cubed plus 27 over x plus 3. So what would we do with this? So obviously uh, we cannot just put in the negative 3 because that will give you an undefined. But what we really need to do here is we really need to factor out x cubed plus 27. So if you don't know how that works exactly, just remember that we have this general thing for the plus version of the x cubed, where we have the first thing cubed plus the second thing cubed equals to just the x plus the y, so that basically the cube root of them multiplied by, of course, this would be the x squared. You can think of this as that, and minus the xy, and then also plus the y squared. So you can use this to kind of figure out it if you're not 100% certain how to factor x cubed plus 27. So let's rewrite the limit then, and let's try this. So if we were to do this, how would we factor it? Well, we know that the cube root of x cubed is x, and the cube root of 27 is 9. So we can kind of do this from here. So we know it'll be x plus 9, or I'm sorry, x plus 3. And then it would be x squared, and then it would be 3x, so minus the 3x because we're dealing with the x and the y multiplying by each other, and then also plus the 9, so our 3 squared. And that's a way you could factor it as well. You also could just test things out and you would eventually get it, but this is the faster way. What can we do now? Well, we can cross out these x plus 3's. We then can go ahead and rewrite the limit a little bit, and we can get that we're going to get in this case, we've actually canceled out the denominator. Instead of, usually it's the other way around, so we actually can just rewrite it as a polynomial. And now there is no problem with plugging in negative 3, so we can very easily put in negative 3 here. So this would be negative 3 squared minus 3 times negative 3 plus 9, which, of course, if we went ahead and wrote it again over here, we would get that would be 9, and then negative 3 times negative 3 is also 9 again, and then plus just this 9, and then 9 plus 9 plus 9 is the same thing as 9 times 3, which is 27. So the answer to this limit actually is going to be 27. So this is very similar to the factoring one, the one that involves maybe like x minus 5 over x squared minus 25. The difference is that there's a cubic, and it's just a little bit longer to do. So it's important to realize that they can give you a cubic graph, and it will give you just the same thing. So just keep in mind that they could give you something like a cube to factor and then cancel, but the process is still the exact same. Next, I wanted to do another radical one and test that process out as well. So when we're doing radical problems, it's important to always remember the conjugate. So let's just say we had the limit as x approaches, let's just say 0 of the root of 3, let's just say plus x, and then let's minus that from root 3, and then let's have that all over x. So obviously we cannot plug in 0 because that would give us an undefined value, but we can take the conjugate of it. Remember, the conjugate is just a fancy word for whatever the root expression is. We're going to take the opposite of it. So that would be 3 plus x, and because this is a minus, we're going to take the plus version of it, so we're going to have a plus in the center instead, and we're going to multiply it to both sides of the expression so that we're not actually changing the value of the expression, we're just kind of manipulating it, just like always. So if we were to rewrite this, what would this look like? Well, we have to kind of FOIL the top. So if we multiply root 3 plus x by root 3 plus x, we'll just get this is 3 plus x because the roots will cancel. If we do root 3 plus x multiplied by root 3, the negative will stay there, but we'll have root 3 multiplied by root 3 plus x. And then if we did root 3 times root 3 plus x, well, this would be a plus now of root 3 times root 3 plus x. I know it looks a little messy right now, but this is actually what you want. And then we'll have root 3 multiplied by root 3, which will just give us a negative 3 because the roots cancel again. So now we're left with this kind of large foiling thing on top, and we're going to keep everything else on the bottom the same. So we're going to keep the 3 plus x plus the root 3. We're just going to kind of carry it down. And I know it's tempting to FOIL this out too, but whenever you have a root problem, a square root problem, you never want to factor or FOIL out the bottom. It will work itself out if you just leave it alone. So as you can see, the root 3 and the root 3 plus x are opposites of one another, so we can actually these will cancel each other out, which happens all the time when you take the conjugate of whatever root you're dealing with. And let's say that we could rewrite this now as 3 plus x minus 3, which is what we have left over, and then we have the x times the root 3 plus x plus the root 3. So what can we do now? Well, if you notice, the 3's can now cancel. So if you notice, everything starts unraveling, which is the whole point of this, because we're trying to see if we can rewrite this to a better way to simplify. So the x is on top now only, and we have an x multiplied by root 3 plus x and plus a root 3. So what can we do now? Well, this is why we didn't FOIL it in the beginning, because the x's end up canceling themselves out as well. And if you recall, the x was actually the problem, because we can't have the x being a 0 multiplying everything on the bottom. So now we just have a 1 over really everything, the thing we originally multiplied. So the root 3 plus x plus the root 3. And what we want to do now is, if we notice, the actual thing to plug in isn't an issue anymore. So we can very easily plug in the things here, and because we're plugging in, we don't have to rewrite the limit anymore. So we can say that this is going to be 1 over root 3 plus 0 plus root 3. And of course, the 0 just makes this a 1 over root 3 plus root 3. But just like all numbers, let's just say you had like 1 plus 1. Would you leave this as just 1 plus 1 in your answer? You wouldn't. You'd want to put these together. So just like how this equals 2, this would equal 2 root 3. We're not done either, technically, because we don't usually like leaving roots in the denominator. We want to multiply it by root 3 to put it back up top. So we'll get root 3 up top, obviously. Now, root 3 times root 3 we know is just 3. The roots cancel. And 2 times 3 equals to 6. So the whole answer to this limit is root 3 over 6. Now, it's important to realize that technically this is the same answer as 1 over 2 root 3. We're just trying to simplify it a little bit to have it a more useful, a more formal answer. But the answer is still the same. And if you notice with these root problems, you are doing the same thing quite a lot. The only difference is you are trying to basically get your conjugate to be usually on the bottom, and that's what your answer usually is going to turn into. But there's a lot of simplifying that has to happen. So now that we've kind of figured out how to do a pretty difficult, I would say, radical problem, now we're going to try what's called rational problems. Now, if you don't remember, rational is just another word for a fraction. So it's a fraction, usually within a fraction are these problems. So we'll have the fraction, but then there'll be little mini fractions. And we obviously can't have that as an answer, nor can we use that very well trying to find limits usually. So let's just say we had something like the limit as x approaches, let's just say it was, 3, and it's going to be the 1 over 3 minus 1 over x, and that's going to be over x minus 3. So what do you notice here? Well, just like before, if we were to plug in 3 here, we would get a 0 over 0, which we can't have. So, but for rationals, we don't take the conjugate of it. We take what's called the common denominator of it. So we would be multiplying it by the common denominator of 1/3 and 1 over x, which would be 3x. So we're going to multiply it by 3x, and what we'll end up getting is we're going to do this to cancel out the mini fraction so that we just have one fraction to deal with. So if we have the 3x, and if we multiply that over to the 1/3, we'll get 3x over 3, and so the 3's will cancel, and we'll be just left with the x. So the x will be left with here, and the 3 will be left with here. And then we'll have an x minus 3 on the bottom, and we're not going to FOIL this just like before. We're going to leave this be, just leave it as a multiplication. And if you notice, the x minus 3 and x minus 3 can be canceled now. So then we'll have the limit as x approaches 3 of 1 over just 3x. Now we can do something. We don't have that pesky x minus 3 on the bottom now. We can plug in. So 1 over 3 times the 3 will give us 1 over 9. So this was kind of a more straightforward rational expression, but if you notice, it seemed really difficult to do if we didn't understand how to use common denominators in this problem. So a lot of these limit simplification is understanding what strategy to use at the beginning so that you can cancel out things and then plug in eventually at the end. Now let's try something similar, but let's try something that doesn't actually look like you have to do that right away. So let's pretend we had the expression, the limit as x approaches 0, let's say, of 1 minus e to the negative x, and it would be e to the x minus 1. What would we do here? Well, if this doesn't look like the same thing from before, it's just because it's written in a way that's a little bit, it's trying to misdirect you. So if you don't remember, if we had any sort of answer, let's just say we had 2 to the negative x. Well, the negative x tells you that it needs to be in the denominator. So really what we're dealing with here is 1 over 2 to the x. This is the same thing. So they're kind of trying to make you not realize that we are dealing with fractions just the same. So let's apply that theory to this e here. So if we applied it to this theory, we would have 1 minus, and we would have 1 over e to the x. So remember, we're just rewriting it. We're not doing anything but rewriting the same thing in a more convenient way. Now, does this look a little more like what we found before? A little bit, but the 1 may be throwing you off. So let's write the 1 as 1 over 1, which is the same thing. Can we do it now? It does look like it now. So if we have 1 and e to the x, what would be the common denominator here? Well, it would just be e to the x, because the 1 technically would be there, 1 e to the x, but it doesn't change anything, so we can just say it's e to the x. So let's multiply both sides by e to the x, and let's see if we can't start canceling out things at that point. So e to the x times 1, we will just get that that's going to be e to the x, because e to the x over 1, and then 1 over e to the x, well, that would be e to the x over e to the x, which is just 1, so we can write that as just 1. And then we'll have e to the x minus 1 multiplied by e to the x. So e to the x minus 1 over e to the x minus 1, this looks just like the other problem. So we can cross out these e to the x's, and we'll be left with the 1 over the e to the x. So let's just say it's 1 over e to the x. Now, can we do it now? We can do it now, because there's no e to the x minus 1. So if we were to plug this in, we would get 1 over e to the 0 power. What is e to the 0 power? Well, that's just equal to 1. So we have 1 over 1, and 1 over 1 is just 1. So the answer to this whole problem up here is actually just 1. So that's the importance of understanding negative exponents and that kind of thing. It's a bit of a trick problem, but actually once you understand the trick, there isn't too much confusion. You just have to write it in a way that's familiar to you. So that's why I wanted to show you that kind of problem, because it can throw off students just because it doesn't exactly look like your problem set right away. So now that we've gone over a lot of the more confusing ones, we've gone over the limits where there's cubic functions, which means you can solve the same thing with quadratics pretty easily. Cubics are just a harder version of that. We've done a pretty difficult radical problem. We've done a pretty difficult rational problem, 2 of them in fact, one of them being a trick question. We're going to end off by doing a pretty convoluted or interestingly written sine special limit trig problem. So if you recall, the limit as x approaches 0 of sine of x over x is equal to 1. And if you also recall, we also know that the sine of u over u is also equal to 1. So this just means that anything, if the x's are the same, so if it's like 3x and 3x, that would also work as well. So knowing that, if we know that, let's do kind of a more tricky problem, because before in the past, it's pretty intuitive how to do them when we do have sine right away. But what if we had something like a tangent instead? So what if we had the limit as x approaches 0, and let's just say it was 2 tangent squared of x, and this was over your x. What in the world would you do here? Because we don't have any sines to deal with. We don't even have a cosine. So what do we do? Well, this is just a matter of rewriting something that's purposely written to you in a weird way. Just like when you had those e's, it's much easier if we rewrite this. So if you recall, we can rewrite tangent as sine over cosine. So let's do that. So let's just rewrite the same thing in terms of sine and cosine. So this would be 2 sine squared of x over the cosine squared of x. And that would be all over the same thing as before. So I know it looks like we're making things worse, but this actually will work out. So if we were to do this, create get rid of this complex fraction. So in a sense, we would basically multiply by the cosine over x, because this is like a 1 over cosine of x. We would be able to, so like a cosine basically square root of x, if we were to cancel out this complex denominator and then do it down below, we could rewrite this as the limit as x approaches 0, and we'd be left with the 2 sine squared of x, because we canceled out this one from before with this one. And we could also then say that that's going to be, so if we multiplied the bottom by cosine squared, just like we did in those other problems, we're just rewriting the same thing. We're adding basically a 1 over 1 here. Well, then it would be the x times the cosine squared of x. So the cosine is just being multiplied essentially by the bottom. Does this make it a little easier to solve? Kind of, but it still seems a little far off from our original definition. Well, with these special limit problems, you always have to rewrite something so that it's a little bit more easy to see. So we know that the sine of x over x is kind of what we want, because we want it to cancel out to 1. We know that's going to be something we're looking for. So let's just do that then, right? Let's just break up and let's just right away say that we want the sine of x over x. and let's just do everything else after. So if we were to do that, what's left over? Well, we know we have a 2. We know we have a 2 left over because we took that out to make the sine of x over x. What do we have? Well, we have two signs here. We have a sine squared, so we know that's going to be a sine of x left over. And we also know that the only other thing we used, because we used the x here to make sine of x over x, we have a cosine squared of x. So let's just rewrite all of that. So if you notice, we didn't really do anything. We just broke up the fraction and multiplied it together, which is perfectly fine because if we were to multiply this out again, we would get this same thing. So this is perfectly, you can do this perfectly fine. There's no issue. Can we do something with this now? Well, let's see. Let's see if we can't do something with this now. So let's see what this would equal. Well, we know that the limit of x approaches 0 of sine of x over x, this is just 1. So we can say this is 1. So this right here turns into 1. Let's see if we can plug in 0 and if it makes it undefined. Because we couldn't plug in 0 here because this would be over 0, which didn't work. But let's see if this works now. So 2 sine of 0 over the cosine. Remember, the cosine squared is just saying that the whole thing is squared. You can rewrite that, or you can just know that, of 0. So let's see what that is. So we have 1 still. What is sine of 0? Well, sine of 0 is just 0, and 2 times 0 is also 0. So we just have a 0 on top. How about cosine of 0? Well, cosine of 0 is 1, actually, and 1 squared is just 1. So we actually just have 0 over 1. Now, is this a problem? No, because 0 over anything is 0. The problem is when we have something over 0, that's undefined, and that can't happen. But we can have 0 on top. That's fine entirely. So 1 times 0 over 1 is basically 1 times 0. And then 1 times 0 is just 0. So hilariously, this whole problem is just equal to 0. So let's just say we had something like the limit as x approaches 2 from the right, which remember, this is just saying from the right of a graph or the right of a function, so that's all that's saying. And let's just say we had this kind of interesting, weird thing. We have x squared, so far so good, plus 3x, and let's just say we had 1 over x minus 2 squared. So what would we do here? We have kind of a weird looking graph going on of functions. This seems to be the part that's bothering. So to solve this, we have to rewrite everything in terms of its own limit. So let's do that then. We have to break it up essentially, and this will allow us to solve this problem. Now, wherever you have something like this, where we know that this will result in infinity, usually the answer will give you some sort of infinity. But we have to show our work, otherwise we won't get credit for doing something like this. So let's just say we're breaking up the limit, and this is perfectly fine. We're just going to be breaking each one up in its own limit. So the limit as x approaches 2 to the right of the 3x, and then the limit as x approaches 2 of 1 over x minus 2 squared. So if we wanted to graph x minus 2 squared, you could do it perfectly and it would work too. But let's say we wanted to find the graph of x minus 2 squared. Well, we know that this is essentially saying that we have a x point at 2, and because this is the point where x would be undefined, we know that the asymptote is that x is equal to 2, which means that other than that, we also have to know this is an x squared graph. And we know the x squared graph has these two going up in the same direction if they're positive. So it looks basically like this. Okay? And in that case, if we knew the graph, and we're saying it's the limit as x approaches 2 from the right, so from this side, if we're going. So if we're approaching the right and then going up forever, well, that would mean that we're going up to positive infinity. So if we were to do that, and I meant to put a minus sign here, we know that the answer for this one is positive infinity. Then we'll know that we can now kind of plug in everything else. So these other two weren't the problem. So if we were to plug this in, this would be 2 squared. This would be equal to 3 times 2, and we're going to subtract whatever we got from this answer. And we know that from our graph, that was positive infinity. So let's now do this further. 2 squared is 4. 6 is 3 times 2. And minus a positive infinity will just give you a negative infinity. Okay, so 4 plus 6 minus infinity, so whenever you have infinity and some numbers, infinity is way bigger than any of this, so we just end up getting that the answer is negative infinity. So just remember that it doesn't really matter if you're multiplying them, dividing them, in most cases, adding, subtracting, the negative infinity usually will kind of consume the other answers. So that's why our answer is negative infinity. Now, the last thing I want to do is kind of do one that's a little bit interesting, because it's I want to do something like a log function. So let's say we had the limit as x approaches 3 of, let's just say, the ln, which is, remember, log base e, of, let's just say, x minus 3. Is this a normal function I can plug in something to, or is this a infinite function? Well, let's do the graph very soon, but let's first just ask the question, what is the ln of 0? Is that something that exists? Well, it turns out the ln of 0 doesn't exist. We know the ln of 1 would be 0, but the ln of 0, it's a DNE. It doesn't exist, which means that this is an asymptote. But we also can just graph it and see it that way too. So if we had a 3, which is the point that is the asymptote here, we make the asymptote kind of like here. We know that the log function looks generally like this, so it's going to look a bit like this. So if we had, basically, let's just say 3 from the right, and it would have to specify from the right, because from the left, the log function doesn't exist. But from the right, we would know that it's going to go down to negative infinity, okay? So this would be negative infinity, which means the whole answer to the problem would also be negative infinity as well. So there's a lot of problems like this where they may look like they're simple and don't require any sort of understanding of the graph or if it's infinity, but always keep in mind, try to test whether or not the answer is defined or if there's an asymptote somewhere, and that will tell you if there's an infinity or an infinite discontinuity in play. So this was just a few pretty difficult, I think, examples with analytical limits, the practice layer algebra skills, as well as solving limits that way as well. So I hope this helped. Thanks for watching.